Hello. Today I'm going to look at an extension of an application that we saw earlier, the basic application, area under a curve. We're now going to talk about area between two curves. In the basic result, I was looking at a function that was non-negative and the x-axis. In reality, we can think of the x-axis as the second curve. And so this is really the area between two curves where the bottom curve is y equals 0. Kind of basic. We now, instead of having, well, I still want that. Instead of having now my bottom function being y equals 0, I might have a bottom function that does something like this. And so, rather than deal with the area under a curve, I'm now going to deal with the area between these two curves. And so in this particular situation, the area would be the integral from a to b of f of x minus g of x dx. What is happening here, we would take vertical rectangles between these two curves. Remember what we did before. Let's suppose I use the left-hand endpoint to get my height. My height of this rectangle is now the top function minus the bottom function at whatever I pick. Take the limit as n approaches infinity. We get an integral just like before. The important part of this is that this is always the top function. This is always the bottom function when we're dealing with finding an area using vertical rectangles. So if my function does something like this, let's suppose that I have a function that does this. Let's suppose that this is f of x and this is g of x. And let's suppose that this is a and this is b. And I want to find the area between these two curves in this sort of bow tie area. We would have a point of intersection at point C, and the way we would have to do this area is it would be the area from A to C, and in that region my function f of x is the top function, plus, and then we would have the integral from C to B, and in this region, my function g of x is the top function. So we would switch around. This would be g of x minus f of x dx. And we have to calculate both of these values separately. Okay? There's also a situation where my functions are not functions of x. And so instead of looking at vertical rectangles, we might have the situation where I want the area between curves like this. And now these are not functions of x, but they are functions of y. And so let's call this function f of y, this one g of y. And in order to determine this area, what we would do is actually fill in this area by looking at rectangles that go horizontally and work from the bottom to the top. And so if this value represents y equals c, and this value represents my y value of d, in this case my area would be the integral from y equals c to d of f of y minus g of y dy, or right function minus left function. It's always the more positive minus the less positive. Top minus bottom, right minus left. If we're going with vertical rectangles, my variable is x. This is x equals, and it's top minus bottom. If I'm going with horizontal rectangles, my variable is y, and it's right minus left, and the functions are in terms of y. Okay, let's look at some specific examples, and hopefully this will make a little bit more sense. Suppose I have y equals 3 to the x, y equals 2x minus 1, x equals 0, x equals 2. I want the area between these four curves. And if we wanted to, we can draw a graph. This is the exponential 3 to the x. We don't need an exact graph. I just need a rough sketch of what's going on. We don't really need that, but that kind of helps. Y equals 2x minus 1. Y-intercept is -1. Slope is 2. X equals 0 is the y-axis. X equals 2 is over here somewhere. And so, this is kind of the region that we're dealing with, and I want to fill this in with vertical rectangles, which means my area is going to go from, since this was x equals 0, this was x equal 2, x goes from 0 to 2 of top function 3 to the x minus bottom function 2x minus 1, which then gives me 1 over the natural log of 3 times 3 to the x minus the antiderivative of 2x is x squared. This is a plus 1. The antiderivative of that is plus x, evaluated from 0 to 2. And so then we would get 9 over ln of 3 minus 4 plus 2 minus 3 to the 0 is not 0, it is 1. 1 over ln of 3 minus 0 plus 0. And then we would end up with 8 over ln of 3 minus 2. Generally speaking, I'm not going to work out the actual numerical value. I'm just going to stop here and let you can figure out what the numerical value would be. That's called executive privilege, so I will not finish them up. Okay, second example. Suppose I have y equals 1/10 x squared plus 1/10, and y equals x minus 2, and I want the area between these two curves. The first one is a parabola that opens upward, kind of wide. The second one is a line, looks like this, and so this, let me exaggerate this a little bit. This sliver of area is what we're looking for, and in order to determine that, if I want to use vertical rectangles, I need to know the x values at these endpoints of that area. So what we can do is, to find those x values, we need to know when these two equations are equal to each other. And so I will set them equal and solve. And so in this case, first thing I'm going to do is multiply by 10, or then x squared minus 10x plus 21 is equal to 0, which factors nicely. X minus 3, x minus 7, and so my x values are 3 and 7. And so this area then is the integral from 3 to 7 of the top function, which was the line, minus the bottom function, which was the parabola. And then we can work it out. And again, I'm not going to work this out completely. I will take the antiderivative. But this becomes x, well, let me do it this way. Negative 1/10 x squared. I get a plus x minus 21/10 You have to leave the tenths. We're not solving an equation. You can't get rid of that. The antiderivative in this case then becomes negative 1/10 times 1/3 x cubed plus 1/2 x squared minus 21/10 x, evaluated from 3 to 7. And again, I'm not going to finish that out. Okay, next example, I want to look at one that goes sideways, where we use rectangles that are horizontal, my variable being y instead of x. And let's suppose that I have x is equal to y squared minus 2y plus 3, and x is equal to 2y squared minus 5. And I know both of these are sideways parabolas that open up to the right, the top one being wider than the bottom one. Let's suppose I didn't want to graph these, or I didn't want to take the time to figure out the graph. Other than that, I want the area between these two curves. We really can do this without having a graph. Because I want the area between these two curves, I need to know where the two curves intersect each other. And so I will go about solving like I did before. And so this gives me then y squared plus 2y minus 8 is equal to 0, which factors nicely. Y plus 4, y minus 2, or y equals negative 4 and 2. So I know these two curves intersect when y is negative 4 and y is 2. What I need to determine is which one is further to the right, which one is the one to the right, which one is the one to the left in that region. And so what I can do is pick any number I want that is between negative 4 and 2 and put it into the two functions. So let's suppose that I pick y equals 0. For the first one, the end result comes out to be 3. For the second one, the end result comes out to be negative 5. Therefore, the first is the one to the right. The second is the one to the left. And so my area then becomes the integral from y equals negative 4 to 2 of the right function, y squared minus 2y plus 3, minus the left function, 2y squared minus 5 dy. And again, I will do a little bit of this, but not all of it. This is now negative y squared minus 2y plus 8. And so when I take the antiderivative, I get negative 1/3 y cubed minus y squared plus 8y, evaluated from negative 4 to 2. And whatever numerical value that comes out to be. I want to do one more example. And in this example, we're going to actually calculate the area two different ways, using both vertical and horizontal rectangles, thinking of it as functions of x and also as functions of y. So let's suppose I have y equals the square root of x and y equals 1/2 x. So again, this is pretty basic. We have the square root function and y equals 1/2 x. This is my basic area. If I set these equal to each other and solve, I get x is equal to 1/4 x squared, or 4x is equal to x squared. Do not divide by x. That would be really bad. Instead, set equal to 0 and factor, and we get the two solutions, 0 and 4. So in this case, these two curves intersect at x equals 0, obviously, and at x equals 4. And so if I were to think of this in terms of vertical rectangles, filling this in, which is the natural way in this particular situation, I can find this area by the integral x goes from 0 to 4 of top function, which is the square root of x, minus the bottom function, 1/2 x, which then gives me, I'll actually finish this one out, the antiderivative of x to the 1/2, 2/3 x to the 3/2, minus 1/4 x squared, going from 0 to 4, which is, the square root of 4 is 2, cubed is 8, times 2/3 is 16/3, minus 4 squared is 16, divided by 4 is 8, minus 0 minus 0, and so we get 4 squared is 16, divided by 4 is 4. I can't divide. There we go, that's better. 16/3 minus 4 minus 12/3 is 4/3, and so the end result comes out to be 4/3. Now, another way I could have done this problem is I could have looked at this in terms of rectangles that went horizontally, like that. And instead of going from x equals 0 to x equals 4, as we did originally, now I'm going to go from y equals 0 to y equal 2. Right? If I substitute these values in to either one of my equation, x equals 0 corresponds to y being 0. X equals 4 corresponds to y being 2. And so if I want, I can actually look at this as rectangles that go horizontal and calculate the area from right function minus left function. And so my area in this case is going to be the integral from y equals 0 to 2 of the right-hand function. Now, you have to be careful here. When I say right-hand function, this has to be a function of y. And so the line is the right-hand function when I'm looking at it horizontally, but the line I need to convert, and this is the function x is equal to 2y. The left-hand function is the function x is equal to y squared. It's a parabola when we go sideways, or the top branch of a parabola. And so now we would get the right-hand function, which is 2y minus the left-hand function, y squared. And this is the same area, so hopefully we're going to get the same result at the end. It shouldn't matter which way we do this. This is y squared minus 1/3 y cubed, evaluated from 0 to 2, which gives me 4 minus 8/3, which is 12/3 minus 8/3, 4/3. Get exactly the same result. There are going to be times when we have to switch how we view an area. Sometimes, even though it's originally given to us one way, we're going to have to switch and look at it the other way. It may be given to us, as in this situation, vertically, and I want to look at it horizontally, or vice versa, given to us horizontally, and we'll have to look at it vertically.